So acid, base, neutralization reactions. An acid, anything that starts with hydrogen, and our bases, so we already know what an acid is because we did acid nomenclature. Our bases are going to be an alkali or alkaline earth metal paired with hydroxide. So let's look at an example. This is kind of our stereotypical acid-base reaction. Hydrochloric acid reacting with sodium hydroxide. It's going to be a double replacement reaction. All acid-base neutralization reactions are double replacement reactions. Okay? And we're always going to make a salt and water. Let's take a look. So we're going to take H plus, pair it with OH minus, and we're going to take Na plus, pair it with Cl minus. So my first product is HOH. We're going to talk about that in a second, hydrogen hydroxide. And then my next product is NaCl. Everything's plus one, minus one, so it went great. But if we look, what's hydrogen hydroxide? Well, that's H2O. We usually don't write it as hydrogen hydroxide. We usually write it as water. Now, this was an aqueous solution of hydrochloric acid and an aqueous solution of sodium hydroxide. And they combine to make liquid water. And then if we apply our solubility rules, sodium chloride is aqueous as well. Why did I put a liquid for water? What state of matter is water in at room temp? It's a liquid. So that's why we put a liquid there. And it's a cursive L. So what we just did here is no different than what we were doing for predicting the precipitate. We did a double replacement reaction. We predict the products. We applied the solubility rules. That's aqueous. And water is a pure liquid. So what happened here? First thing I want you to notice is we made a salt, and a salt is a synonym for ionic compound. This is actually table salt. So this is like when you say the word salt, this is what you're thinking of probably, right? And then water. So all acid-base neutralization reactions create some salt and water. Now, if we write the complete ionic equation for this, or total ionic equation, we're going to break this up. This would break up into H plus and Cl minus and Na plus and OH minus. So there's my reactants. Hydrogen cation, chloride, sodium cation, hydroxide. You do not dissociate the water. This is like the solid in a precipitate reaction. You're going to keep that together. Okay, so keep the water together. That's a pure liquid. It's not aqueous. We only dissociate aqueous things. And then this is aqueous. So we get Na plus and Cl minus. And now if you look at this a little closer, chloride and sodium, they are spectator ions. And my net ionic reaction is actually always the same for acid-base neutralization reactions. All acid-base neutralization reactions will have the same net ionic equation. It's H plus OH minus goes to H2O. H plus OH minus goes to H2O. Now I want to prove this. So I want to do one more. And I want you to see that no matter what acid and no matter what base we pair together, you're going to have a net ionic equation that is H plus OH minus goes to H2O. So let's have you try another one here. Why don't you try this guy? Why don't you take, I don't know, why don't you take hydrobromic acid? and allow that to react with, I don't know, potassium hydroxide. So acid, alkali metal with hydroxide. Predict the products. Give me a total ionic equation. Give me a net ionic equation. Go ahead. All right. So hopefully H plus OH minus, you wrote water or HOH, right? And then potassium plus 1, bromides minus 1. Hopefully you wrote KBr. And that's going to be a 1, 1, 1, 1. You don't need to have the ones. For the
Question.
complete, yeah, what's up?
Why did you write the H2 as aqueous and not liquid?
Because I messed up.
Okay.
Thank you. Appreciate you catching that. I really do. Yeah, that should be a liquid. Thank you. Thank you. Thank you. Thank you. So now we need to do the complete ionic equation. And that's where we break apart these aqueous guys. I forgot to write aqueous here too. So we're going to break that apart. So we got H plus and Br minus. And then we got K plus. We go to OH minus. Essentially what we're saying is we're going to mix this mixture of 4 ions together. The H plus and the OH minus find each other to make liquid water. And then the K plus and the Br minus, they stay aqueous. So they don't change. And since the potassium and bromide were dissolved in ions on the reactant side and they're dissolved in ions on the product side, they're going to cancel out. And you can see we get the exact same net ionic equation we had before. H plus AQ plus OH minus AQ goes to H2O liquid. And there we have it. I know. Okay, we got to cover molarity here quick. And then we're done with new stuff for the night. So we're just going to do molarity. I got some molarity slides, but it's going to we'll at least introduce it here on the board. So molarity is a chemist's preferred way to represent concentration. So let's talk about concentration. Concentration tells you essentially how much stuff is dissolved in your solution. So how much solute is in my solution? And chemists, there are many ways to represent concentration. If you take Chem 102, it's actually what we start with. Okay, but the preferred way for a chemist is to use molarity. Molarity is abbreviated with a capital M. And it is the moles of a substance divided by the volume in liters. So N stands for moles. You say, wait a minute, why didn't they use an M? M is taken, that's mass. So they pick the next letter, moles. And then V is volume. And that volume has to be in liters. So if you see a solution, it says 3.5 molar hydrochloric acid. That means there's 3.5 moles of HCl in 1 liter of water. Let's calculate a molarity. I'm going to give you the easiest problem like all year. So I want to know, what is the molarity? So molarity equals question mark. If, well, here, I'll write it out as a sentence. What is the molarity if 3.15 moles of sodium chloride is dissolved in, let's do 2.75 liters of solution? So it's like literally as easy as it could get. We plug the 3.15 in, so molarity equals 3.15 moles divided by the volume, 2.75 liters. divided by 2.75. 3 sig figs divided by 3 sig figs. That would be a 1.15. The 4 rounds up. Then we would do a capital M for molar. And then we write the identity of the solute, NaCl. So a solution that contains 3.15 moles of sodium chloride in 2.75 liters of solution, that would be a 1.15 molar sodium chloride solution. Obviously, maybe you can start to, if you think really hard, you can see how this is going to get more difficult. Instead of me giving you the moles, what if I give you the mass? Well, then you'd have to convert that to moles using the molar mass, right? What if I gave you the volume in milliliters? You'd have to divide it by 1,000 to turn it into liters. Let's look at a problem like that. So what is the molarity if 8.550 grams of potassium chloride is dissolved in 285 milliliters of solution? So molarity, moles per volume. Let's get that numerator first. Here's what I need you to do. I need you to convert that 8.550 grams of KCl into moles of KCl. Go ahead. You should get 0.115 moles of KCl. That's going to be my numerator. Oh, I'm so sorry. 4 sig figs. 0.1147. So if you like that leading zero, 0.1147 moles. And now we need to divide by the volume, but the volume has to be in liters. That's a requirement for molarity. It must have units of moles per liter. So you need to divide that by 1,000, right? So if you want to show that with dimensional analysis, 285 milliliters, 1,000 milliliters in a liter, that's 0.285 liters. So 0.1147 divided by 0.285. 4 sig figs divided by 3 sig figs, 0.402 molar potassium chloride. 0.402 molar potassium chloride. All right, let's do one more. I'll show you how it's like a twist. We can do dimensional analysis or algebra with this. Let's try this. How many grams of, well, let's do sodium chloride, are dissolved in 75.0 milliliters of a 4.5 molar solution. I should give this a shot. You can approach this algebraically or with dimensional analysis. See if you can't think your way through this. All right, let's do an algebraic approach to this problem. So molarity is moles per volume. We have the molarity. So that's 4.5 molar. Volume we sort of have. It's got to be in liters. Let's divide that by 1,000. That's 0.0750 liters. So we have that, 0.0750 liters. We can solve for the moles. And if we get the moles of sodium chloride, then we can take it to grams. Is that easy? So let's plug and do some algebra. So 4.5 molar equals N over 0.0750 liters. Capital M is an abbreviation for moles per liter. It's an abbreviation for a more complicated unit. So watch, when I multiply by 0.0750 liters, the liters cancel out, and I'm left with moles, which is good. So 0.0750 times 4.5. And we get 0.33. We got 2 sig figs, so 0.34 moles of sodium chloride. And now I could take that 0.34 moles of NaCl, and I can multiply that by the molar mass of sodium chloride, 22.99 plus 35.45 is 58.44. So 0.34 times 58.44, and we are going to get 20 with a decimal point grams of sodium chloride. So what we just, yeah, what's up?
You got the 0.34 for the moles of sodium chloride. Would you just keep, like, I was always taught to just keep the number.
That's totally fine. Yeah.
Mhm.
You do not have to round the sig figs till the very end.
Okay, cool.
Now you might have got 19 then or 21, right? And that's fine. I'll still take that. Yeah.
Fair enough.
Yeah. Sometimes if you don't round the sig figs till the very end, you're gonna, but as long as you have the right number of sig figs, so 21, 19, I would take that. Yeah. So this is like the algebraic approach to this problem. It's fine. If that makes sense to you, do it. It is kind of messy. Let me show you the dimensional analysis approach to this. Maybe you'll like the dimensional analysis approach. This is the last new thing we'll do. Same problem, but check this out. If we do 4.5 moles of sodium chloride per 1 liter, because that's really what capital M is, moles per liter. If we multiply that by the 0.0750 liters, liters cancel out and I'm left with moles. So taking a concentration times a volume in liters gets you an amount in moles. And then you could just go right into 1 mole of sodium chloride has a mass of 58.44 grams. And look at that. It's like so clean compared to what we just did, right? I mean, dimensional analysis is pretty sweet if once you get the hang of it. And we get the same answer now. Yeah, again, this time it rounded to 20. And there's the other thing, Elliot, with this method, yeah, you're not rounding till the end, so it's cool. So if you don't round to the end, you get the same answer with rounding.